Okay, welcome everyone to our course on microcontrollers. This is the first uh, lecture which will be focusing on the introduction, examples, and applications relating to this particular topic of our interest. As we always emphasize during our courses, the one which we teach, uh, specifically which I teach, I emphasize that whenever you read words um, which you do not have kind of prior knowledge about the meanings of that word, I encourage uh, to visit, Google it, or go to the Oxford Dictionary, Cambridge Dictionary, and read about the history of those words, because the history of those words gives immense, enormous information which will be extremely beneficial to understand not only the word but why it started and and what's basically inside that particular word. It may be related to technology or something else. So for microcontrollers, that will be our first focus, is to understand what this word is. Micro, I think it's pretty common um, English word. It means something which is small. A controller is something which controls things in the world of electronics, digital systems. We want to control um, uh, things, and we will see in our examples and application what those things are and how we can achieve the controlling functionalities. So that's what microcontrollers as an overview, but we will see the details as we go through this presentation. So all of our courses were delivered through Contact Field Institute. Anyone interested in seeing what we do, kindly visit the LinkedIn profile, or you can contact us through the given email addresses. I really like to emphasize HS Clouds. HS stands for Humanity Serving Clouds, and that's exactly what our intentions are, is when delivering courses. Okay. So again, as mentioned right in the beginning, so the focus is what is a microcontroller, and most commonly when you talk to a technical individual or a person or an engineer who has worked on microcontrollers, the reply would be that it's an IC. That is the most common reply you will get from a technical individual who has worked on microcontrollers, microprocessors, DSPs, whatever, or something technical. So an IC means it's an integrated circuit. Okay, so integrated is kind of a common word that we collect things. That's what this word we use for. The important thing for us to understand here, that what is a circuit? So circuit is basically connecting basic electronic components in a fashion, in a way, using a technique to achieve a certain functionality. Okay, like for example, in this circuit, it's a passive low pass filter. Don't worry about it, what it means. That's not the purpose. But we have connected a resistor, R for resistor, and a capacitor in this fashion to achieve the functionality of a passive low pass filter. Or you can just simply remember this as a functionality, and we can write this as that this circuit does achieves a function C1. So we can just write it like this to make it easy to understand. Similarly, if we connect the same two components in this way, we achieve this, what we call it as a passive high pass filter, or we achieve a functionality C2. So this circuit is basically circuit C1 achieving a functionality FC1. This circuit C2 achieving a functionality FC2. So similarly, we can connect resistor, capacitors, inductors, transistors, transformers, and other components together to achieve functionalities. And this is some of the basic, it's simple to see and understand the kind of functionality which I am showing. So here, you can have so this is basically a simple single-ended general purpose amplifier using a transistor, and we denote this as functionality N. So in between we have a lot of functionalities, from functionality 1 to functionality N. So these are all circuits, different circuits, C1 to Cn. Okay, so our purpose is that how we can integrate, how we can combine all these circuits together. So in a mathematical form, what we say is this is the integral single. If you don't know, in mathematics that will be used for integrating. So our purpose is that all of these circuits we want to combine, we want to sum it together in a small package. We call it as an IC, which is integrated circuit. Mathematically we can represent it like this, and or we can also use a summing single symbol to combine these circuits in one package. And to do that, we use what we call it as IC manufacturing technology. Okay, and so that's how these ICs look like, and most of them, these are surface mount ICs. You don't need to worry about it, what that surface mount mean in this particular lecture, but just to show you that that's how the ICs can look like. Okay, and that's how small it can be. So this is on a finger, and all the rest of the ICs here, you can compare it with a coin. So these are very basically tiny packages, and in this package we have many circuits of our interest. Okay, but in relation to microcontrollers, when we talk about, because microcontrollers mostly deal with digital circuits, so when we talk about digital, they have circuits which implements these gates. Again, these are some of the basic gates. We will learn about these gates in the subsequent lectures, but for this particular presentation, what you need to understand, but when we talk about microcontroller ICs, since it's a digital IC, so the digital circuits are implemented in these sort of packages, and these are some of the basic logic gates: NOT, AND, NAND, OR, NOR, exclusive OR, and exclusive NOR. And why not take this opportunity to make it even simpler, that if you remember the name of this NAND IC, you can build any digital circuit by simply using NAND gates. And yeah, so just for now, just remember this. Okay, so let's continue on to our next slide. And the IC packages can come in different forms and shapes, as you can see here. We are not going to go through all the names that this is just to show you that the packages, the IC packages, integrated circuits, comes in different forms and shapes. Let's go to the next one. Again, continuing with the same thing, many forms and packages and pin counts. But since our focus is on microcontrollers, so this is what you can see, that the microcontrollers can be as tiny as this one. Okay, and this is also a good picture which I found. These are the PIC 10 series microcontrollers, You can see that um, uh, it can be a we call it as a through hole, because as you can see these are legs, okay, and these legs will only go through a hole in order to fit it on a breadboard or on a printed circuit board. That's why we call it as a through hole. Whereas this tiny microcontroller is an SMD, surface mount. You can just place it on a surface and then solder it. We'll go through the details subsequent, but here in this particular slide, the only thing that I need to show you that the microcontrollers ICs can be as small as this one, and can be big, as we have seen in previous slides. Depending on the number of functionalities you need in a particular IC package or a microcontroller IC packages, um, the size gets bigger and bigger. So let's go to the next slide. Okay, so now it's important, since we are now understanding the basics on integrated circuits, or in this sense in particular microcontrollers, I think it's important to understand how these packages are manufactured and what is the fundamental which component or what are the fundamental building blocks of manufacturing or making such packages. Okay? And this particular slide we're going to talk about a very brief history, not without going into the precise technical details. We're just going to give an overview of the history. So everything started with vacuum tubes back in 1904, and the purpose of these tubes that they were amplifying electronic signals, electronic connections. So they were used for amplification of electronic signals. Because of vacuum tubes, it led to the invention of transistor in 1947, AT&T Bell Labs, and this is the shape of, or the look of the first ever successful prototype of a transistor. They were using germanium metal or a material for their experimentation or prototype work. That successful prototyping invention led to the explosion, I'll say exponential growth of using transistors, rather vacuum tubes, again because of disadvantages and disadvantages of using vacuum tubes, size, power consumption and other stuff, and the advantages offered by transistors. It led to more and more use of transistors, and what you see here is basically the evolution of from vacuum tubes to transistors in different sizes and shapes, which basically led to populating these transistors on a silicon chip using the methods developed, and that's why that's how the integrated circuit or ICs terminologies started. And that's the different symbols we use for a transistor without going into the details. So these when we make schematics or circuits using for different purposes in electrical or electronic circuits, these are the if you are using a transistor, depending on what type of transistor we use, we pick up we use the proper relevant symbol to show it on our diagrams. Okay, again very quickly, It all started with the invention of vacuum tubes in 1904, which led to, because of the disadvantages of using vacuum tubes, more and more efforts were put into to make something similar functionality but in a more compact and kind of a advantageous way, which led to the discovery or the invention of a transistor at AT&T Bell Labs in 1947, and the evolution led to making ICs, the integrated circuits. And on an integrated circuit, what we do is basically use techniques to design our circuits on this particular package. In case of digital ICs, the fundamental building block of digital ICs is transistors, and these are the different symbols of a transistor depending on what type of transistor we are using. Okay, now hopefully it basically give you a good overview on digital ICs and microcontrollers and integrated circuits. So these are CPU ICs risen from AMD, and the basic building block is a transistor. On any digital ICs is basically a transistor, and more transistor we can squeeze in, we can achieve enormous power in a small package that we couldn't have done if we just stuck with using vacuum tubes for the purpose as a transistor. Okay, and this is the Intel Core i9, and the growth and the power lying on digital ICs or carried by digital ICs is basically follows what we call it as the Moore's law. We will talk about it as we go through in this particular course. Let's go to the next slide. Okay, so I think now you hopefully have a clear understanding of what is an IC, what is the fundamental building block of digital ICs, and now it's a good time to introduce that what is a microcontroller. Okay, as I mentioned, my microcontroller is simply an IC, like a package. It's basically a digital IC, and mostly, I should say mostly it's a digital IC, because nowadays it does offer other analog related functionalities like capturing an analog signal or transforming a digital data into analog output, and we will talk about it as we go through the course. So in a microcontroller, the brain of this IC is a microprocessor. Please keep this in mind. Like we humans, we have a brain. This microcontroller IC, as a package, the brain is a microprocessor. Okay, we as humans, depending on how many languages we can speak or understand, we have a lot of okay. So this is kind of a graphical view of an Arduino Uno board. That's how it looks like, and as you can see here, from pin 13 we are connecting to this resistor, and this resistor most commonly is going to be few ohms, maybe 100 ohm or so for current limitation. And this is the LED. So on an LED, the important thing is to see you need to understand the shape of this LED. This rectangular side is basically, we call it as an anode. It's a plus side on an LED, and this bar is basically is the negative side. So when you physically hold an LED, like in this case, when you hold it, the anode side is a longer leg, but in this picture you see this notch, a little notch, that also shows that it's an anode. Okay, so what we are doing here, pin 30, the wire comes to this breadboard, and there is a separate I think a video available on the portal where you can understand what the breadboard is. So when we connect here, these all holes are connected together, so that's why it's connected with this resistor, and this resistor is connected with this anode side of the LED, and the other side is going to ground, as you can see here. So that's which basically completes the connections using Arduino Uno. Okay, so now we need to write a program, and to write a program we're going to run the Arduino IDE. This is how an IDE look like. We will make a new sketch. Okay, so this is file new. This is kind of the window will look like when you open up a new sketch, and this is exactly what we're going to write here as mentioned in the previous example. Okay, so setup will only runs once, and as you can see here we are setting the pin mode 13 to an output pin, okay, as discussed before. And in the loop what we are doing, we are writing to pin 13, or we are making pin 13 high, then we are giving it a 1 second delay. 1000 millisecond means 1 second, and then we're making it low, and then again a 1 second delay and going back, and this will go on, and that's how the thing blinks. Because what's going to happen, let's go back here. So when this pin becomes high, high means it's positive voltage or plus, let's assume that's plus 5 volts. So plus 5 traveling, kind of a, I shouldn't say traveling, but there will be a current flow from plus 5 to the ground, and because of that the LED will glow. When this side is 0, there won't be any current flow, and that's why it will be off. So after every 1 second this LED will be blinking on and off. So this is the example of a blinking LED using Arduino IDE. Okay, so we discussed the simple block diagram of a general purpose microcontroller, but some of the powerful microcontrollers have many blocks inside them. Okay, as you can see here, A to D converters are basically called as analog to digital converters. They converts analog signals to digital, so they are part of powerful microcontrollers. Similarly, DAC stands for, which is not mentioned here, DAC stands for digital to analog conversion. Some microcontrollers also have DACs in their package. Okay, more RAM, like oscillatory circuitry inside there, or depending on, and as you can see here, the SPI, I2C, kind of a ports, serial communication ports, USR is very common, and timers, PLL, as you can see, PLL stands for phase lock loop. So what I want you to get from this particular slide is that the more packages, the more IC packages or functionalities you integrate on a microcontroller package, it makes it powerful. And that's how a powerful microcontroller can, kind of features it has, and kind of it looks like as a block diagram. Again, this is an example of an ARM. I think it's a 64-bit Microcontroller can be 8, 16, 32 or 64-bit. I myself was quite surprised. Just recently read about it. In my opinion, I was just thinking that maybe up to 32-bit I knew, but 64. Then when I found that there were 64-bit microcontrollers, then I literally I searched for 128-bit microcontroller, but I couldn't find any as of now, as I'm recording this particular video. But you never know, the requirements can always change. So more blocks, more power consumption, more size of an IC means powerful microcontrollers. Ideally, engineers, scientists want to see power squeezed to the minimalistic IC package with the least amount of power consumption. Again, dreams, but you never know. Dreams can also come true as well. That's how all technology starts. That you have a dream, you work on it, you don't achieve that what you envisioned, but you make a progress towards those objectives. Okay, these are again some of the example of powerful microcontrollers block diagrams. And again, these are, if you click on, PDFs will be shared with you. So you can, as you can see, once you have the PDF, you can just simply click on these block diagrams and it will take you to the link from where the information is taken. And this block diagram of a microcontroller for space applications. So in space, we cannot use an ordinary general purpose or even industrial use microcontroller we can buy. It has to be space grade IC package. Microcontroller, as we already know, is just one of the IC, because it has to carry with enormous radiation, so that's why they are very costly. Okay, so let's talk about more applications of my microcontrollers, and I'm just showing you here a vehicle. It can be a gasoline vehicle, hybrid, or electric. Irrespective of that, all these features you see here are microcontroller driven. So I'm not showing you one application example. I'm showing you many application examples of a microcontroller where you can use it. Okay, so it's very powerful using microcontrollers, again because it's small, easy to use, easy to program. These are some of the core reasons of using microcontrollers. Okay, so without going and just reading all those, please take your time and read about it. I'm going to make this thing simple for you. Whenever we are designing a system using a microcontroller, microprocessor, or a DSP, or even I can say any other, when you're designing a system, we can simplify it like this. Any system we design, what we are doing is basically we have an input block, then we have a processing block or an intelligent block. In our case, it's a microprocessor or a CPU, and then we have an output based on what we want to do here. You talk about a car. Let's take this car as a system. So what is the purpose of a car? Okay, what is the input of a car? The input of a car is a gasoline, because the key purpose of the car is to go from one place to another, right? So its input is gasoline. Okay, because of the gasoline we can start the car. Okay, the intelligence is provided by, we are not talking, let's talk, okay, so we can talk autonomous vehicle, but rather than talking in autonomous vehicle, the CPU or the microprocessor in conventional cars is human. Okay, because it does the navigation control of the car to go from point A to B. In case of autonomous vehicles, the entire thing is controlled by the system's design, which has basically a lot of inputs, a lot of sensors to make sure that it safely goes from point A to B. Again, the output is basically driving the vehicle and traveling the distance. So that's what we do. Any other? I think because of the amount of time I have, there are many other applications I can discuss in relation to this particular slide and the features mentioned here. But as I mentioned, I just want to make it simple, and the simplicity is that any system you design, this is your simple blocks what you need to worry about, and there may be inputs, maybe one to maybe thousands in a complex system. This processing can be done by one CPU, multiple CPUs, or like a combination of CPUs and FPGAs, and the output again can be one or can be many. Okay, so let's carry on with our to the next slide. Oh, so one important thing what I wanted to mention here is that some complex, quality, efficient systems have a feedback mechanism where the output gets fed back into the intelligence for further control on the quality outcome of the overall system design. So this basically completes the three building blocks, and this feedback mechanism, we call it as, makes it an efficient design of the system. So let's go to the next slide. So this is another example of using microcontrollers for fluid level sensor application. So it can be any fluid, but in this case we are taking care of water. We are considering water. So it's an overhead tank in Southeast Asia or in Africa or other warmer countries. What people have is they have a water well nearby or within their vicinity of the house, and this is the motor connection to extract water and bring it to the top or to the roof of the house where the water tank is. Okay, so normally what happens is when people early in the morning basically start the motor to fill up the tank without any automation, so they manually turn on the motor for required amount of time. Again, that amount of time is depending on their experience to fill the water tank so that it can last for a couple of days, 1 day or whatever. Okay, so the entire purpose behind this particular application is to auto fill the tank as the water level goes down. Okay, so how it happens, so here these are the aluminum wires, okay, going inside the water tank. The plus 5 volts DC also connected with the water tank. I don't like it. I don't like this way of achieving the fluid level sensing application. One way what I can tell all the students or listener or audience is that keep one thing in mind, that there are always multiple ways to achieve a certain objective. Okay, in this particular case, this sensing, we are using 4 sensor wires, which are aluminum wires, and connecting it in this particular fashion to achieve the functionality of fluid level sensing, but it can be multiple other ways we can achieve the same thing. But anyhow, let's discuss on this particular way of implementation as an example. So since water has conductivity, and because of that conductivity, as the level comes up, because of this wire touching the water, or this wire, or this wire, okay, all of these four wires, whenever the water touches that one particular wire, the current flows through their respective resistors, and because of that current flow, one can detect voltage levels on these analog inputs. So these are Arduino Uno analog inputs connected with the analog to digital converter. So the program which we have written for the microcontroller, it will be continuously monitoring these ports for the level of any digital change. When I say digital change, the analog to digital converter inside will be providing the data on these respective ports. Whenever there is some high digital value on the respective port, it means the water level is at that particular level. Okay, so for example, if there is some digital read or digital data coming from A4 line to the program, it means the tank is full. If there is no digital data or least digital number, it means it's less than full, less than 3/4, less than half, or less than 1/4, and a time to turn on the motor. Okay, so the program, what it's doing is continuously monitoring all these analog inputs, and depending on what we want to do, we want to turn on the motor here, or we want to turn on the motor here, as soon as and that turning on of the motor at half tank full, or quarter tank full, or 3/4, one can have other inputs as dip switches to so that we don't have to change the program. We can just simply use dip switch to enable and tell the program that at what level we want to turn on the motor. Okay, so what happens as soon as that level or the level of the water goes below the set threshold, it's going to make this pin high. Making this pin high will turn on this transistor. Turning on the transistor is basically we are turning on the motor, and turning on the motor means that it will take the water from underground, and using the mechanical, the piping system, it's going to pour water inside this particular tank. Okay. The other thing what's mentioned here is a sump tank. It has multiple usage, but you can think this as an extra water source. Okay, and again we are using the same aluminum sensing wire, and whenever there is water, we can indicate as an LED. There is no LED for that connection. This is a power LED, but we can indicate that there is a sump pump level, or we can ring the buzzer. Similarly here, if the water loss goes down below a certain threshold, for the motor to turn on, we can also use the buzzer to indicate the same. And also we can display that information on this LCD, liquid crystal display. 16:2 is the most commonly used industrial or consumer applications kind of a LCD display we use. And as you can see here, we are using the microcontroller serial lines, okay, in order to communicate with this LCD. That's how an Arduino Uno board actually looks like. This is the main microcontroller. Okay, and without going into the details, the entire purpose of discussing this particular application, this for fluid level, is that how a microcontroller is greatly beneficial. So in this particular application, there is no human intervention, and it will automatically fill the tank, indicate the audience, or the household individuals or employees at a certain factory about the water tank levels in the main overhead tank or on the sump tank. And as you can see here, the sensor assembly consists of 4 aluminum wires arranged at quarter, half, 3/4 and full levels in the tank. So let's go to the next slide. Okay, so these are since we discussed fuel level sensing, and this is good to see that how the industrial or commercial fuel level sensors look like. So this is how, as you can see, very rigid, robust, nice looks and packaging of commercial scale fuel level sensors. Okay, this is the sensing element, and this is also the sensing element. We don't have time to go inside the details, but as the course progresses, we will discuss about this industrial or commercial level sensors as we discuss the prototype versions or we do the prototype versions in our lab experiments. Okay, as mentioned before, microcontrollers also used for space applications. So these are the space grade microcontrollers. It has to be rad tolerant, means the radiation tolerance is very important. Radiation hardened MCUs and MPUs, and highly reliable. The important thing to share this particular size. The main important thing I wanted to share is that the microcontrollers or any other IC going into space has to be radiation hardened and radiation tolerant. Okay, that's the most important thing. And these companies' names I wanted to share, that these are the approved vendors of silicon manufacturers which manufacture radiation hardened or ICs for space applications. Okay, Infineon Technologies, EPS, Microchip, Renaissance, Silicon Labs, ST Microelectronics, Virago Technologies. Okay, so let's go to the next slide. Okay, so as a career objectives and the course objectives in this particular slide is to get comfortable with using any microcontroller for potential application needs. So we are going to practice with 3 or 4 microcontroller kits. Arduino is one, Raspberry Pi is another one, but I will pick another maybe from ST or Microchip to make you guys comfortable of using any I'll say any microcontroller, but potentially popular microcontrollers for your application needs. And we will try our best to make you a good embedded firmware developer for industrial or consumer applications. These are the course objectives, and become a better digital circuit or system designer. Okay, the PDF which is shared with you, I would like all of you to go through these links and see the entire videos in its entirety. Because shortage of time, what I'm going to do, I'm just going to show you a few videos here which I already. So this is these videos are going to show you the use of microcontrollers for in different applications. So here you go. So as you can see here, this is an autonomous vehicle, and a microcontroller is only a small fraction of an application in this particular scenario, and there will be many microcontrollers in this system, the neuro vehicle what you're seeing here. But just to show you that how the commercial applications of using a microcontroller will look like. But in this particular case, this vehicle is using navigation sensors, cameras, so it's basically using DSPs, FPGAs, microprocessors and processors, in my opinion, in its entirety. The very well known intelligence ICs in order to design a system like this. Okay, and as I mentioned, microcontroller is only a fraction of a use in such a quality design. As you can see here, it's auto navigating, and based on the number of sensors it has, and the complex firmware, I shouldn't say complex, but highly efficient quality firmware and related software in order to achieve the objective of autonomous pizza delivery. Okay, that's enough. Let's go to the next video. So this video is I'm going to go back here and so this is the air delivery, air autonomous delivery of monitor the sensors. Okay, so all those the reason of showing these videos is that where potential microcontrollers can be used. And again, this is I really like this, it's a combination of all these videos which I am showing you, AI, ML, AI, artificial intelligence, machine learning, deep learning, and microcontrollers, DSPs, microprocessors, FPGAs all together. So again, as I said right in the beginning, microcontroller is only a fraction used in these applications. So as you can see here, this is that's amazing. Display of technology in the air. I'm sorry, it's taking time to load. Cool. Close a few of the tabs to okay, so let's see this particular video as a microcontroller application.
To established approaches, a true scientist can develop more economical and environmentally friendly technologies. For example, finding a way to capture more solar energy without increasing the surface area of solar panels. Inventor Andre Bracel set out to collect the maximum amount of energy from both solar and even lunar light. The result of his work is the transparent sphere beta A, which, like a lens, focuses the solar flux on a photovoltaic cell.
So as you
Due
can
to the
see,
dense and stable
control
flow
of
of
that
light,
motor
the small
is
sized
basically is the use of the microcontroller.
solar module delivers power comparable to that of a large battery. To catch the brightest rays and work in low light conditions, Beta A features a motorized sun tracking system. The electric motor rotates the photovoltaic cell block on two axes, and the solar module is precisely positioned on the sun with the help of cameras. The sphere can be used like conventional solar panels to increase a building's energy consumption, and potentially as a charging station for electric vehicles. Another interesting proposal is to use this technology as window-like devices that collect solar energy.
So as you can see, it's basically
Although it may take some
this
time to get
technology is
used to the
relating to capturing maximum sun or moonlight in order to charge the batteries and for using it for residential, commercial, or for vehicle charging. Okay, so since the video is taking too much time in loading, so I'm just going to the next video, and this time I think I should refresh in order to avoid. No, I don't have to refresh it, and it should be okay. So here's another example. Cool system, and that cool system is basically a humanoid. I'm just going to refresh it so that it's preloaded rather than we just wait. And I'm going to do the same here so that we don't have to.
I forgot my tools again.
So the guys were working and forgot some tools on the ground floor. So he's sending instructions. He's sending instructions to a humanoid designed and built by Boston Dynamics, a very well-known kind of a company in this particular area. Let's see what this thing is going to do. This humanoid, what it's going to do. So the microcontrollers is not in my opinion a possibility of not having a microcontroller used in such a system as well. So that's why I'm showing it here, that where the microcontrollers can be used. How they have used it, I don't know, but whenever it comes down to consuming less power, more efficient processing, dynamics. When I say chip, I mean IC, and you know IC means integrated circuits. It's taking that much time. It's slow. See? that's what a really cool system is. Anyhow, so I think, as I mentioned, I really encourage all the students to go through each link and explore all of these, kind of really cool, neat applications where the microcontrollers can be used in kind of commercial, industrial um, systems. Okay, and here's the list of projects which are basically microcontroller based. I'm not going to go through the list, but it's just going to mention you that it's basically everywhere. And if you click on this link, here's the reference of this link, which has the details relating to these projects. Okay, so in this particular course, here's the distribution of marks. 10% assignments, 5% before midterm and 5% before final. Lab work is 20%, and this 20% is not attendance. This 20% means it's a 1 hour exam on midterm day, before midterm paper exam, and 1 hour exam before final on the finals paper exam. Okay, so that's how the 20% will get allocated to you as lab work, because we want to make sure that you understand, you not only understand, but you can demonstrate that you have done good in this particular course. Midterm is 30% and the final paper exam is 40%. And along with that, I'm mentioning here 4 industrial trips, and but it can be less potentially. And the idea behind that will be visiting companies manufacturing or assembling plants using robotic systems or any other kind of systems where potential use of microcontrollers can be demonstrated. And so we highly encourage all the students to be part of these field trips. Okay, so this is regarding how the course will progress. And the preliminary course requirement is the high school, college, decent knowledge of logical reasoning and problem solving. As long as you have this, you can do this in this particular course, because we are not expecting or assuming any prior knowledge other than this in order to do good in this particular course. Being good in mathematics or physics is always seen as a very nice kind of a base to do good in potentially many fields. Okay, having a basic understanding of programming is not assumed, but having a basic understanding can really help you do good in this particular course. So as we discussed before, here's again a kind of a block diagram of a microcontroller showing main components, and this is the block diagram I took from Microchip. This is one of the Microchip SPIC 12 series microcontroller. So I'm just going to go over some of the important details, technical details, which we'll further explore in the subsequent lectures. As we mentioned in the beginning, in one of the basic block diagram, is that CPU or microprocessor is the brain in a microcontroller. Okay, so CPU is the brain. Okay, a CPU in a microcontroller can be an 8-bit, 16-bit, 32-bit, or 64-bit. And that when we say that the CPU is 8-bit, 16, 32, or 64-bit, what it means that the registers inside the CPU, the size of those registers are of that size, and the database which CPU can connect with, the size of that database is 8, 16, 32, or 64-bit. So remember this, it's not the address bus, we are talking the database. Whenever we are mentioning the database size, whenever we talk about whether it's an 8-bit microcontroller or 16-bit microcontroller, 32 or 64-bit microcontroller, or a CPU. Doesn't matter. Either way, we are mentioning the size of the data bus. Okay, and as you can see here, the CPU is connected with different peripherals, its internal peripherals, through this, the size of the data bus. Okay, so these are memories. Okay, it's a program memory. Again, it's a memory. SRAM. S stand for static RAM. We will discuss in more detail when we talk memories. And again, we will talk this program counter is primarily basically a fetch, decode, execute kind of a, in relating to that particular process is the program counter. We will discuss further in detail. I'm just giving you a high level overview. Internal oscillator is basically inside this chip, microcontroller chip. It generates 8 megahertz relating to this particular block diagram. So there are circuitry which can generate an 8 megahertz square wave. So that's what we call it as an internal oscillator. Internal voltage reference circuitry, brownout reset, BOR for brownout reset, WDT stands for watchdog timer. We will discuss what those means, why we use it. 10-bit ADC is analog to digital converter, which is 10-bit. It means whatever the analog signal coming into this ADC gets converted into 10 bits, basically digital data, and it has 4 channels in this particular IC. Comparators means it's an op-amp. Again, we will discuss it, what the comparator is and how to use it. Briefly, basic we will discuss relating to comparators, but since this course is about microcontrollers, so our focus will be on digital side of the rather than the analog side. Okay? But we will cover whatever the kit we will be using and explore all the blocks of that particular kit. Obviously, the analog capturing and comparator will discuss the basics. Capture compare, PWM stands for pulse width modulation, and we will discuss it again. This pulse width modulation means that this is a square wave and how to modulate it. And these are the timers. In this particular block diagram, there are 2 8-bit timers and 1 16-bit timer. So again, just to give you an overview of commercially available microcontroller from Microchip, and discussing as an overview the block diagram of that microcontroller. Okay, let's go to the next slide. So this slide shows the popular OTS, as the term stands for off-the-shelf microcontroller kits. This is expressive systems. I really like this kind of a kit. They sell modules or kind of kits like this, and I have used both. I have used the modules, and I've also used kits for commercial industrial applications. What are the key advantages? All in one kind of a scenario. You can do digital, you can do analog, you can do Bluetooth, you can do Wi-Fi. And the kit, the programming environment is you can use Arduino IDE, or they have their own, but anyhow, Arduino IDE style kind of a programming environment. You can use Arduino IDE. I have used Arduino IDE to program these expressive microcontroller kits. Very easy, very powerful library, so you can do a lot in small amount of time. Okay. So let's accidentally I clicked here, so that takes you to the website. So I'm going to reload it and I'm going to relaunch it. So that I get the full screen. Sorry for that inconvenience. So this is the Raspberry Pi, which we will be using in this particular course as well. Again, a very popular kind of a kit, microcontroller kit people use in various industrial, commercial, prototype style of applications. And these are the Arduino boards. I showed you this picture in the beginning of slides, but there are many variations of Arduinos. That can be as tiny as you can see this boards. So yeah, so these are the boards. We will be working with Arduino boards, Raspberry Pi, expressive systems, and also a kit from Microchip and ST Microelectronics as well, to give you enough kind of a base to do good, not only in this course but also in your future endeavors relating to employment.